In this video, we're going to talk about the idea of factoring. When we factor, what we're actually doing is undoing multiplication. So in this video, we'll do one type of factoring called greatest common factor. So when we factor, what we're actually doing is taking multiplication, as you can see here. Oh, I got to get a good marker here. We're taking this multiplication, which we have done, and we go down to this trinomial. So when we factor, we're going to take this trinomial, or whatever we have factored, and we're going to bring it back to where we started. What greatest common factor can do is simplify your equation, your expression or equation, and to make it easier to then do other types of factoring. So when we look at greatest common factor, that's a preliminary for many other types of factoring. So when we factor, there are a number of things that we can do. In this video, we're going to talk about the first two, greatest common factor, and I usually abbreviate greatest common factor GCF, meaning greatest common factor, and then kind of an offshoot of greatest common factor is factoring by grouping. So with greatest common factor, you're usually factoring out a term or two. In grouping, you're factoring out an expression like an x plus 2 or an x minus 5. Then later we will do trinomials, and we're just going to do the simpler one when that first term is equal to 1. Now when you factor, just like when you are working with fractions, you want to keep factoring until you can no longer factor. Just like when you reduce a fraction, you keep reducing as much as you can. If something is not factorable, then it's prime. So you're not guaranteed to be able to factor everything. So we can move on to greatest common factor. Now what we see here, we're going to work with these two rows. What I want to look at is the first row, and we have three sets of terms. I'm not worried about how they're connected. I'm not worried about any numbers in front of them. I just want to look at what would be a greatest common factor. So when you do a greatest common factor, you look at every component of each term and to determine is there something common in each of them. So for example, if I look at the x's, so I have three sets here. We have an x to the fourth, x squared, and x cubed. So if we write this out expanded, x squared is x times x, and x cubed is x times x times x, and then x to the fourth has four sets of x's. And what we want to do is we want to look to see what is common between all three of these. And if we look at these, I'll circle the first set of x's and the second set of x's. So what's common here is x squared. So that'll be one of the first greatest common factors. If we look at the second, look at y for instance, we have y to the 8th, y to the 7th, and y to the 5th. And if we write it out expanded, we'll find that the y to the 5th is the greatest common factor. It's the greatest number of factors that are common in each of the terms. And the next one is z. I'll just underline that 3 times, make it easy to see. And we have the same thing. We have z to the 10th, z cubed, and z cubed. So the greatest common factor, meaning what do they share, is z to the 3rd. Now if we look at the last letter, you can see this w. This w doesn't reside in the other two terms. So that is not a greatest common factor. So in this instance, what we will be factoring out is x squared, y to the 5th, and y cubed. Now the next example, scroll this down a little bit, we want to look at not only the coefficients, 2, 4, and 8, we want to look at a, b, and c. So if we look at the coefficients, 2, 4, and 8, the greatest common factor is going to be 2. If we look at a, the greatest common factor is just simply an a. We have a squared, a to the 4th, and a. Same thing for b, and same thing for c. So when you do a greatest common factor, you're not going to find factors on everything, but you can at least use some of them to help simplify things. So we can apply this to polynomials, and we have two examples here. So if we look at this particular polynomial, we have a 5x cubed, a minus 15x squared, plus 25x. So we want to look at each of the coefficients, any signs as well, and we're going to factor out, I'm going to write it over here, a 5. That's, of those three coefficients, 5 is the greatest common factor. And if we look at the x cubed, the x squared, and the x is the only greatest common factor. So then to complete our factor, we have to have something left over. So what we're really doing is we're taking each of these individual terms and we are dividing by 5x. And we know that when we divide, oops, forgot the x here. We know that when we divide terms, we subtract powers. So the first one, you'll see the 5's cancel out, and one of the x's cancel out. So this would be, after factored, would just be x squared. In the next one, we have 5 and 15, so we have minus 3. We can cancel out the x, and we're left with just simply ax. So this will be a minus 3x. And in the last one, 5 and the 25, that gives us 5, and the x's cancel out. So it'll be plus 5. Now the beauty of working with any sort of factoring is you can always check to see whether or not you have factored correctly if you just go through and multiply through. So we'll turn to green. So if I take this 5x and I multiply it through, we get a 5x cubed, we add exponents when multiplying, minus 15x squared plus 25x. So as long as this matches what we started with, then we know that we have factored this correctly. Now while you should check it, especially if you don't feel overly comfortable with factoring, it's not an actual requirement. Now in the next one, we have a minus 16t squared plus 32t plus 32. There's really no variables to factor out, but what we can factor out is a minus 16. We like to have this first term, whenever possible, be a positive, especially later when we do some more complex factoring. So what we're going to do is take and divide everything by minus 16. Now as you do these more often, you might feel more comfortable, and you may not need to actually write these out. So the minus 16 cancels out, so we're just left with t squared. The 32 divided by minus 16 gives you a minus 2t. Do be careful of your signs here. And then the 32 divided by will give us again a minus 2. Now at this point, we may or may not be able to continue factoring. We would look at what's left over and see if we can factor this, and we really can't do anything else, so this would be as much as we can factor. But later, if we were going to graph this or solve it, what's left behind, this stuff, is a little easier to work with. We can get a little more complicated with our greatest common factor. So if we look at this particular example, again, we've got this minus here. We want that really to be a plus. Now, technically, when you are factoring a greatest common factor, you don't have to factor out that minus. It would be correct if you just left the minus behind. But in this instance, we want to factor it out. It makes it easier to work with. So we're going to factor out a minus 15. And then we look at the x's. We have an x to the third, x to the eighth, and x to the 5. So we know that x cubed, or x to the third, is our greatest common factor. And if we look at the y's, double underline them, we have a y squared left. So we can pull that out. If there wasn't a y in that third term, then y would not be something we could factor out. So the first one, we actually just factor that all out. We can just put that at 1. The next one, we're going to take the positive 30 and divide it by, and again, you don't have to show it like this, but as you work through these, you might find it's a little easier to work with. So x to the 8th divided by x cubed is x to the 5th. Again, you subtract. And then y to the 4th divided by y squared gives you y squared left over. So close that. Oops, not done yet. And then we got to do the last one. Minus 15 x cubed y squared. So that'll leave us a minus 4. The x to the 5th divided by x cubed gives us x squared. And the y to the 10th divided by y squared gives us y to the 8th. Remember, when you divide terms, you subtract. Now make sure that you close that out. Now, a lot of students think that, oh, when I divide that out, that 1 is not necessary. It is necessary because, again, if we multiply these through, we can get back to what we started with. And if you did not have that 1 there, you would not be getting back to what you started with. When we work with greatest common factor, we can actually have expressions be our greatest common factor. So if we look at this particular expression, we really don't have a single term, but we have a multiple term. My pen's not working. There we go. So if you look here, we have an x plus 7 and an x plus 7. So what we can do is factor that out. So we'll factor out an x plus 7, and then we'll leave the 11 plus 3a behind, and this would be factored. In the next one, we have the y plus 9 and the y plus 9, and we can factor that out. So we have a y plus 9 is our greatest common factor, and then we have all of this stuff and this stuff left behind. We got to put that in one big parenthesis. So I'm just going to write that down. We can simplify in a minute. Minus 2y. And then, of course, as with everything else we do when we work with polynomials, we want to combine like terms. We see the x and the 3x will give us 4x, and the 5y and the minus 2y will give us 3y. And then that would be in factored form. Now sometimes when we work with factoring, greatest common factor, we can't find a common factor for all terms. So if we look at this example, while we have an x in the first term, we don't have x in the, we have x in the first two terms. We don't have x in the other two terms, so we can't factor an x out. Same thing with the y. So what we can do, and this is the idea of grouping, we can look at the first two terms. And if we look at xy plus 5y, we can actually factor out an x. So what we have is x times y plus 5. And we can do the same thing for the next one. What can we factor out between these two? Well, we can factor out a 3. And that'll leave us a y plus 5. Again, when we factor out a 3, we're dividing this by 3, so we get 3y divided by 3, just leaves us y. And 15 divided by 3 gives us 15. And then you'll notice we have a y plus 5 and a y plus 5. We can factor that out. Plus 5 times x plus 3. The order of these binomials does not matter. We could write it, if you wanted, x plus 3 times y plus 5. Either way would work. In the last example here, Same as before, while we might have 3's here and 2's here and oh, we have a bunch of x's, they're not anything common. So what we have to do again is look at the first pair and the second pair. So the first pair we can factor out a 3x, and that leaves us an x plus y. Now since we're attempting to factor this, hopefully these last two terms we can factor out and get a y plus x plus y. So here we can factor out a minus 2, and that also will leave us x plus y. And now we have another greatest common factor. So this would leave us x plus y times 3x minus 2. And that would be in factored form. So that is working with greatest common factor. The idea is to look for a factor that appears, the greatest common factor that appears in each term. Now even though later when we start solving these, it won't matter if you factor out a 3. So for example, if I had 3 times x squared minus 4x plus 2, that's an x by the way, the 3 later when we start solving really won't matter, but to be correct we have to have that 3 as part of our solution. So that is factoring greatest common factors.